Hi, this is Nick Pizzi. This is part 2 of the practical math exam for distribution system operators. This is part of our 3-part series designed to help operators prepare for the exam questions involving math used in distribution systems. This comes complete with a schematic, a design, and operational data. As I mentioned, this is part 2. If you haven't seen part 1 yet, at the end of this video, there will be a link that you can click on to bring you there. Let's go ahead and get started with part 2 now. Share that with you. Again, this is Practical Math Exam Distribution System Operators, Part 2. We're going to review the data that I gave you on the last one, but briefly, because I went through it in detail. You should really go see in Part 1 if you want to get through it a lot. But this is a satellite system. We were designed to serve 5,000 people with 120 gallons per capita per day. And the planned operation of this system was to run one pump at 700 gallons per minute for 15 hours per day. We would fill up the tank, and then in the evening we would shut down the pumps, and the tanks would fill the system up for anybody that needed it. Then in the morning we'd get up and start it all over again. We buy our water from Central City, and there's an agreement to keep our ground level storage tank filled to an elevation of 666 feet. And no, that is not any reference to the devil. I just picked that number out of the air. So operational data for the month of April 2015, we actually served 4,695 people, not the 5,000 that we were designed to do. So our pumpage might be a little bit less. We used 123 pounds of chlorine during the month. We used $870 to run our pumps, electrical use. And our max day was 0.72 million gallons, or 720,000 gallons in one day. But on average, we averaged 0.056 million gallons, or 560,000 gallons a day. Our tap-free chlorine was 0.4 milligrams per liter, and our tap total chlorine was 0.5 milligrams per liter. Our distribution system free and total chlorines are listed there at 0.2 and 0.3. Excuse me. So with that, let's start up with our plan view and our elevation view so that you'll know how we're designing this system. You should take a screenshot of this page if you need it as your reference so that you can see how things are laid out. We have the plan view where we're up in a helicopter looking straight down on the system. We can see how wide things are, but we can't see how tall things are. So we need an elevation view to go along with that, and that's on the bottom part of the dotted line you see there. You see all of the dimensions coming up. You see there's some height differences. We've got elevation differences at the pressure gauge on the pump, on the storage tank, elevation at point A and point B, and then overflow elevation and entrance elevation to the elevated storage tank at the end of our system. So with that, you should be able to work the following problem. We're going to pick up with number 6. We did the first 5 problems through on the first video. So this is the question number 6. And we're asking, what would be the chlorine demand in milligrams per liter if the chlorine residual is the average total residual reported coming out of the pump station for April? So at this point, if you want to work this problem, go ahead and pause the video, work it through with pencil and paper, get your calculator ready to go, and work it out, and then come back. I'm going to give you the answer now. This is how I worked it. And I remember this is a demand problem. So chlorine demand always equals the dosage minus the residual. In other words, the amount of chlorine that we put in versus how much chlorine is left over after, say, 30 minutes or so. That's our demand for chlorine. So we need to know how to calculate a dosage first. So dosage can be calculated by dividing the amount of chlorine used by the pumpage that we had for the month or for the day. So I took 123 pounds of chlorine used in April, and April's a 30-day month. So if we divide by 30, we see that we use 4.1 pounds per day of chlorine in our satellite system. So I went back to the operational sheet and found out the pumpage. We see that our average day, we pump 560,000 gallons, or pump 0.56 mgd. When I work that through, the dosage would be 4.1 pounds per day divided by the 0.56 million gallons per day divided by 8.34. And I come up with a dosage of 0.87 milligrams per liter. That's how much chlorine I put in the water each day. But they're not asking that. They're asking to know what was the demand. So I have to go in and find the residual and subtract it from my dosage, and that will give me the demand. So I did it this way. Put my demand that I calculated 0.87 milligrams per liter and subtracted from it the total chlorine residual, not the free at the plant, but the total, because I want to know all of the demand. So I subtracted it from the 0.87 and come up with a demand of 0.37 milligrams per liter. Hopefully you got that right. Let's go ahead and move on to question number 7. In question 7, they're saying the village suspects sporadic high pressure from central city altitude valve, but the village, of course, has gauges that are out of service, and they're denying that they're having a problem, which is typical. So the village foreman finds an old mercury manometer on the shelf and uses it to find the pressure at the incoming line. Because your gauge is out of service, you had to resort to this old-fashioned method. This is not something you should do to this day. We have different manometers that we use that don't involve mercury coming into contact with the water. This is the way we used to do it back in the old days when I was a young man. So don't do it now. Don't do these kind of things now. If you still have this kind of equipment, you should not be using it. The only thing they tell you in this problem is that the specific gravity of mercury is 13.6. I'm going to show you a drawing here. You see that we've tapped into a 12-inch main. The old foreman, who's a canny old son of a gun, brought out his mercury manometer and tapped into that main. And so he's got mercury on one side with its 13.6 specific gravity, very heavy, pushing against the water pressure. And on the other side, you got the water pressure pushing against the mercury. And the way these things used to work is we would let that thing come to balance. Pressure from one side pushing against the weight of the mercury on the other, and eventually would come to balance on a graduated scale. When he did that, he sees that he has a 36-inch column on the gradation scale. How does he use that information to figure out the pressure? He does it this way. First, you figure out 36 inches divided by 12 inches per foot. You come up with a 3-foot distance that the water pressure is pushing back on the mercury. That's the key. We take that 3 feet and multiply it times the specific gravity of mercury of 13.6, and I'm going to subtract from it the pressure from the water. The 3 feet times the specific gravity of water, which we know to be 1. I'm taking this specific gravity times 3 feet for mercury, subtracting it from water, I come up with 37.8 feet of pressure. I've got to convert that to PSI because that's what they're looking for. And we know that for every 1 PSI, there's 0.433 conversion factor. So I'm taking a 37.8 times the 0.433, coming up with a pressure of 16.4 pounds per square inch. And again, that's the old way you do things. Don't do this at home, as they always say. All right, let's move on to question number 8. Question number 8 says you get a low pressure complaint and the flow and pressure test is conducted on a pipe from point A to point B. When you get low pressure complaints in your system, you always got to go out with pressure gauges and figure out what the problem is. So you're going to take your maps, your gauges, you go out in the system, you locate point A and point B on the map. And here's the test conditions that you subject yourself to. All the side main valves are off, and the distance from point A to point B on the map is 2,000 feet. The pressure at point A is 55 psi. The friction loss at that flow rate is 4.5 feet for every 1,000 feet of pipe. If the flow rate going through that pipe is 1 mgd, what's the pressure at B? So this is going to be a situation where you got to figure out the difference in pressure loss from elevation and the difference in pressure loss from friction loss. So here's how I went about it. Remember, when water is moving uphill, it's going to lose pressure. And the faster water is flowing in a main means more friction loss, so it's going to lose pressure for that too. So there's 2 pressure losses you've got to calculate here and subtract it from the original. The original was 55 psi. So first determine the pressure loss due to elevation and then due to friction. So I went the elevation first. I looked on the map that I gave you and I saw that point A is at elevation 680 and point B is at elevation 710. So there's a difference in elevation there from point A to point B. Water's going uphill from A to B. I expect to lose pressure. I'm going to subtract the 680 from the 701 and come up with 21 feet of pressure. And I'm going to convert that to PSI by multiplying by the same 0.433 that I did in the last problem. And I come up with a 9 pound per square inch pressure loss just because I'm going up to a different elevation. Now, depending on how fast I go there, I'm going to lose more pressure as I go. The faster that water has to get from A to B, the more pressure I'm going to lose. So let's calculate that one too. It said we have 2 units of 1,000 feet, and each 1,000 feet we were losing 4.5 feet of pressure. So if we have 2 units, if the pipe is 2,000 feet long, I'm going to multiply that 2 times 0.45. We'll come up with a 9 psi pressure, or 9 foot pressure loss, which I'll convert to 3.9 psi by multiplying by 4.33. So now I have the original 55 psi. I'm subtracting from it the 9 psi pressure loss and the 3.9 friction loss. I'm coming up with an answer of 42.1 pounds per square inch. Hopefully you got that right. We'll move on to question number 9. Question number 9 is asking, when the elevated tank is 1/2 full, then all of the pumps are shut off. So we're not pumping any water. We got a 1/2 full tank. The pressure at the high service pump discharge gauge is going to read what in PSI? And you can ignore any use from the village. So basically they're saying, you shut your system down. You've only got a tank, you've only got a 1/2 full tank. How much pressure you're going to have at that center point of that pump? There's your tank, there's the elevations. And we are in conditions of static pressure, no pumps running. So the head from the elevated tank is going to provide the pressure for us. Now there's our 2 elevations. The bottom of the tank is 785 feet on the map. The overflow on the tank is 819. But the problem said you're only 1/2 full. So you got to figure out the difference between 819 and 785 and add, split it by 2 and add that into the 785 to get an elevation that you're working from. You know that your pump gauge sits at 641 feet. So the tank elevation at half distance from 819 to 785 is 17 feet. So 785 tank elevation at 1/2 full must be sitting at 802 feet. So now it's a difference of 802 feet to the pump center line. So the gauge pressure, not the atmospheric pressure, but the gauge pressure must be 802 minus 641 or 161 feet. And I can convert that to PSI by multiplying again by the 0.433. And I come up with 69.7 PSI. Okay, hopefully you did well on that one too. Let's move over to number 10. What's the net pressure required to lift water from the pump to the maximum elevation as shown in the design data sheet? And you can ignore friction for this problem. Net pressure. Now that's a very vague way of saying things. I'm not really sure exactly what they mean by that, but we're going to work it through the way I think they mean it, and you can argue with me if you want to later on. I think it's a vague question. It depends on what they mean by net pressure, of course, but here's the way I interpret it. Net pressure is going to be the difference in elevation from the pump to the top of the tank. But also it could mean the difference in elevation from the reservoir to the tank. I'm going to pick one and go with it. I'm going to take the 819, the top of the tank, minus the 641, which is the center line of the pump, and subtract them. I'm going to come up with 178 feet of head. When I convert that to pumps per pounds per square inch, I'm going to get 77 PSI. Now that's the difference in elevation from the pump to the tank. So 819 minus 666 would be 153 feet or 66.2 PSI. That would be the work done from the reservoir to the tank. Hopefully you got that one right. That's a little bit difficult to decipher what they mean. Hopefully when you get these exams, they ask the questions a little bit more discriminately than they do in this particular exam, but this was exactly the way it came off. So hopefully we got somewhere on it. All right, moving on to question number 11. This is a tricky one. It shows up on the exams and everybody has a trouble with this because they don't quite read the problem correctly. It says the interior of 300 feet of 12-inch pipe is uniformly coated with 1 inch of scale. How many gallons of water will a pipe contain? It's an important question because distribution operators got to make sure they understand that as you build up scale in a pipe over the years, it's going to reduce the carrying capacity of the mains. You think about putting a brand new water main in, and you think about what it's going to take today to deliver water to people. And you don't factor in the size of main that you need 10 years from now when there's a 1 inch scale on it, or maybe even more. They'll never have the carrying capacity. It's better to put in a larger main now because it will corrode over time and you won't be able to carry as much water. And here's a good example of how that works. So here's a picture of the water main. Here's a picture of the 1 inch scale. The diameter of the new main was 12 inches, so the radius would be 6 inches. I put that up there. That's the radius before the scale. You can see the red arrows coming in. Shows you the diameter and the radius before the scale is built up. If I look at the diameter of the corroded pipe after I've got the 1 inch scale, this is where a lot of people go wrong. They automatically assume if I started off with a 12-inch pipe and I've got a 1 inch scale, I must have an 11-inch diameter scale. No, you have 1 inch on one side and 1 inch on the other. If you take a diameter, which is exactly halfway through the pipe, you're going to meet 1 inch on either side. You've lost 2 inches. So you've gone from 12 inches to 10 inches, not 12 to 11. And that's where most people fail this problem on the exam. So remember, you're going through a diameter you're going to lose 2 inches of scale because of the scale. So the new pipe was 12, and I'm going to do it an old-fashioned way, but you could just do one calculation. But I want to show you the difference in calculation between a brand new pipe and one that has 1 inch of scale. When I figure the gallons in a 1 foot with a 1 foot diameter, half-foot radius, 300 feet of that pipe, I'm going to multiply the pi times 0.5 squared times 300 feet times 7.48 to convert it to gallons. I come up with about 1,761 gallons of water contained in 300 feet of 12-inch pipe. And when I lose that 1 inch scale over time, and I do that same calculation, now I'm using a 10-inch or 5-inch radius, 10-inch diameter, 5-inch radius. When I do that calculation, you see that I come up with 1,222.9 gallons. So I've lost 1,761 minus 1,222 gallons. That's about a 520 gallon difference over a period of a few years. That's a lot of water loss. A lot of ability to carry water has been lost because of the 1 inch scale. So again, if you have any influence over the people that are designing the water mains going in your system, make sure they understand that scale will take away carrying capacity over the long haul. That's why they ask you this question. They want you to know that. All right, moving on to question 12. How many pounds of 15% hypochlorite will be required to disinfect 800 feet of 16-inch pipe with a chlorine dosage of 100 milligrams per liter? Typical distribution problem. You're out in the field, you're disinfecting some new water main, or perhaps you've had to repair a water main and you have to disinfect it again. And you don't have chlorine in the field, you have 15% hypochlorite. How do you do this? Okay, when I do this kind of a problem and I'm using Clorox bleach, I want to remember to calculate the pounds of pure chemical that I would need first. Approach this problem as if you had chlorine in the field and figure out how much chlorine you would need to do this job. And then all you need to do is take that and divide it by the 15%, you know how much Clorox you would need. So the volume of 800 feet of pipe, 16-inch in diameter, is pi times the radius squared times 800 feet, and then multiply by 7.48 to get gallons. You're going to come up with about 8,185 gallons in that 300 feet of pipe. 800 feet of pipe. So that's, in other words, I would take that 8,185 gallons divided by a million, so I would get 0.008185 million gallons. I do that because now I can use the standard dosage formula for figuring out how much chlorine I need. I set that up as 100 milligrams per liter times the 8.34 times the 0.008185. It turns out that I need 6.8 pounds of chlorine to do the job. Well, I don't have chlorine in the field. I have got Clorox bleach. How much Clorox bleach am I going to need so that I can supply 6.8 pounds of chlorine? Well, I got to take the 6.8 pounds and I've got to divide it by the percentage, which they gave us at 15. So I'm going to take 6.8 pounds divided by 0.15. It comes up with 45.3 pounds of hypochlorite, 15% hypochlorite I would need. All you need to know is the gallons. 15% hypo contains 1.25 pounds of chlorine per gallon. So I would need 6.8 pounds of chlorine times, or divided by the 1.25 pounds. I would need about 5.44 gallons of Clorox to do the job. Hopefully you did well on that too. Okay, we're going to go to question 13. We've got a main break here. You see a picture of a water main leaking in the field. This is a typical distribution problem that you got to figure out how much water have you lost. So they ask you this. You got a main break in the village and it's caused one large pump and one small high service pump to operate at capacity during the 2 hours it took to isolate and shut off the leak. But while this thing was leaking for 2 hours, the tank dropped 2.5 feet and both of these pumps came on and operated. How much water was lost in that period? And you got to remember, you have normal usage. People don't stop using water because you got a main break. So the water that you're pumping out, losing from the tank, is coming from not only the leak, the fact that people are still using water in the system, doing that for the entire 2 hours. So let's figure that out. 2 hours of normal use. I go into my operating sheet and I remember that I'm using 560,000 gallons a day. If I do that for 2 hours, divided by 24 hours in a day, I would come up that the people would normally use 46,666 gallons in those 2 hours. That's on average. That's the only thing I can work with here. So on average, we're using over 46,000 gallons. Well, during that time, I'm working on shutting this main off. It's leaking too. I'm going to convert that tank volume loss into gallons also. So I'm going to take pi times the radius squared, 3.14 times 19 times 19 times a 2.5 foot difference in the tank. That's what I lost during that period of time. Convert that to gallons by multiplying by 7.48. And I see that the tank lost 21,197 gallons. Well, if it did that for 120 minutes or 2 hours, I would lose 176 gallons per minute. That's what the tank supplied. So if I add that to what the people were normally using, I would have the pumps running at 700 gallons per minute plus the 350 gallon per minute. There, I get 1,050 gallons per minute. So the tank plus the pump is going to equal 176 plus the 1,050, or 1,226 gallons per minute during that period. So the lost water is the 1,226 minus the 389, or 837 gallons per minute. And I did that for 120 minutes, that's 2 hours. So I've lost 100,440 gallons lost. Quite a lot of water to lose in 2 hours for a small village like that. Okay, question number 14. Putting this in because my wife worked at the electric company all these years. I want to have an electrical problem for you to work. What's the overall efficiency if one of the large pump units, the usage is 75 amps at 220 volts, and the pump output results in a head of 100 feet? Remember, 1 horsepower is 746 watts. It's a little electrical problem that we sometimes have to work in the water business. You should remember this. The formula is amps times volts equals watts, and 1,000 watts equals 1 kilowatt. So at this point, you might want to shut off and work the problem. Just pause the video. So if I take the 75 amps times the 220 volts, I see that the system would have created a usage of 6,500 watts. So 6,500 watts divided by the 746 watts per 1 horsepower would mean that I developed 22.11 horsepower to get this job done. Well, the horsepower is going to be the gallons per minute times the head divided by 3960 and times the efficiency. Efficiency then would be gallons per minute times the head divided by the horsepower times the 3960. I would come up with an efficiency of about 0.799 or about 80%. So my system overall is 80% efficient because I used that many kilowatts to get the job done. So at that point, you could look at your system and see if it needs an upgrade. Hopefully you did that one correctly. And that's the end of part 2 then. So remember to go ahead and click at the end of this video, the link to bring you to either the first part 1 or the part 3 video, which will come up next. And hopefully you've done a good job on this so far in your learning. Glad to help out. Hopefully very soon we'll have the other video to look at for you. Thanks for tuning in.